Hello everyone. In this video, we present on the topic of analytical models for electric potential, threshold voltage and subthreshold swing of junctionless surrounding gate transistor. Our team name is Niger. First, let we know why we are going for the junctionless transistor because the single gate MOSFET's performance degrades due to various reasons like the scaling of the gate length and due to the gate oxide thickness and also due to the short channel effect. The short channel effect also called as drain induced barrier effect because where the channel length is same as width of source and drain. Here the threshold voltage is not controlled by the gate voltage, instead it is controlled by the VDS. Hence it is also called as drain induced barrier effect. Okay, in order to overcome these problems, MOSFETs like double gate, surrounding gate, and FinFETs are introduced. However, these types of MOSFETs also have certain issues because the doping concentration varies between the source and drain, that is in between the junctions. For smaller dimensions, the ultra short doping concentration gradients are required. This mainly affect during the short dimension. For example, the doping must switch from N-type concentration of 1 into 10 power 19 centimeter inverse cube to P-type with a concentration of 1 into 10 power 18 centimeter per cube within a few nanometer distance. This creates a problem in fabrication of the MOSFETs and also the thermal budget increases. Okay, the junctionless MOSFETs do not have this type of different types of doping concentration because here the doping concentration is similar to that of source and drain. Hence, no junctions are here, and also doping concentration is constant and uniform. Since there is zero doping gradient, no diffusion take place from the source to drain. Because of that, the voltage across gate fully controls the movement of electrons across the source and drain. The devices are basically a resistor in which the mobile carrier density can be modulated by the gate. We know that in conventional MOSFET, it is turned off by applying a reverse voltage, but here the device is turned off by fully depletion of the channel due to the work function difference between the gate material and doped silicon in the nanowire. Here the silicon channel is heavily doped nanowire. The figure shows the representation of the junctionless MOSFET. This slide tells about the nanowire transistor without junctions. The right side picture shows about the schematic view of junctionless nanowire gated resistor. The key to fabricate a junctionless gated resistor is the formation of a semiconductor layer that is thin and narrow enough to allow for full depletion of carriers when the device is turned off. The semiconductor also needs to be heavily doped to allow for a reasonable amount of current flow when the device is turned on. These two conditions imposes the use of nanowire dimension. Silicon on insulator technology is used here to produce the high quality single crystal silicon films with a thickness of few nanometer. After growing a 10 nanometer gate oxides, the nanowires were uniformly doped by ion implantations using a arsenic to dope the N-type devices and BF2 to dope the P-type devices. The current voltage characteristic of the gator resistor are similar to those of regular MOSFET. Figure A shows the N-channel gator MOSFET resistor and the figure B shows the P-channel gator resistor. The gator resistor have full CMOS operation, have no junctions and are made in N plus or P plus silicon nanowires, therefore sensitive to thermal budget than regular CMOS devices.
These devices are uniformly doped throughout the wire from a microscopic perspective. The junctionless device is a gate resistor that Vg equal to 0 volt. The mobility of the carrier is the MOSFET is strongly affected by the vertical electric field. The universal mobility curve shows that the electron mobility is the channel of MOSFET transistor decrease as a function of the effective electric field E, following the law E power minus 0.3. Both inversion and junctionless devices that fabricated using process discreted. The channel length is 1 milli, the gate oxide thickness is 5 nanometer, and the doping concentration is 10-17 centimeter and 10-19 centimeter in the inversion mode and junctionless fit respective. So the transconductance was measured and low drain voltage 50 millivolt and is therefore proportional to the electromobility. Both reverse as a threshold of approximately 0.7 voltage. As gate voltage is increased beyond um, threshold, the mobility is the inversion mode device. So the peak mobility is the junctionless is difficult to estimate for measurement.
In these slides, we look about some information about the threshold voltage and the sub-threshold swing of junctionless surrounding gate transistors. They solved this by using the 2D Poisson's equation without the gradual channel approximations for electric potential, and they verified the results by using the technology computer-aided design simulation tool MEDICI. Okay, we know that the junctionless transistors works in partially depleted region. As silicon radius or doping concentration reduces, the total number of electrons from the ionized donors in the channel will also reduce, and the larger gate voltage is now needed to less deplete the channel, so more electrons are left in the channel to turn on the device. Because of that, with decrease in silicon body radius and doping concentration, there is decrease in threshold voltage. Also, with decrease in gate oxide thickness, there is increase in VTH, and also due to the oxide capacitance increases, because the total depleted channel is directly proportional to the oxide capacitance. The subthreshold swing also decreases with the reduction of L or with the increase of doping concentrations. It also observed that the swing increases with the increase of oxide thickness. Therefore, from this we can conclude that we want to increase the VTH, we need to decrease the silicon body radius or the doping concentration or the thickness of the oxide with the increase of the oxide capacitance. But in order to subthreshold swing, we want to decrease means we needs to increase the doping concentration and also increase the thickness of the oxide. Therefore, one have to choose the proper combination between the thickness of the oxide and the length of the gate and the doping concentration. Thank you.